Okay, so as Brian mentioned, I'm going to give you an overview with a little bit of a focus on remote sensing and how these satellites apply to fire. So these are the things we're going to talk about today for the two main types of weather satellites that are out there. We're going to look at their orbits, their resolution, and I'll be hammering a lot on the resolution part. It says channels, but channels on a satellite are just the different wavelengths. So on board the satellites, there's basically a bunch of filters that filter out everything that the wavelength that they want you to see. And we're not going to go through all of them because there's like 16 per satellite. And some of the channels aren't really that applicable to what you do. So we'll go through a few of those. But in order to understand why the wavelengths that have been chosen are the ones that are chosen, you have to know a little bit about how radiation moves in the atmosphere. And that's two types. Solar radiation, that's just what you see with your eyeball. As it comes down to the ground, it gets scattered around by clouds, it gets absorbed, it gets reflected by the surface. And then the Earth, which absorbs that radiation and then re-emits it as long wave radiation. And I say, and as we're doing that, all through it, we'll mix in applications to fire and smoke. And at the end, we'll just do a little peek. Instead of looking at single channel, we'll just say, well, what else can you do with this stuff? And that will just be a couple of slides. Karen mentioned a lot about, not a lot, but mentioned about questions. The way I'll probably play it is if you have a question, you put it in the chat. I've got a few natural breakpoints where I'll sort of stop for a few seconds. And if Karen wants, she can interrupt me if she thinks there's a really pertinent question that will, help understanding of something I may have not said as well as I could. And if not, then I'll just carry on. So we might cover some questions during and some at the end, and also to let Karen be the arbitrator and judge. So the satellite and its orbits. So as I say, there are two types out there. The first one is the one you always see pictures from if you're watching the news and they show weather satellite pictures. The Geostationary Observing Environmental Satellite, otherwise known as GOES. So it sits out around 36,000 kilometers from Earth. It's over the equator and it rotates with the Earth. So if you were sitting on the Earth and you looked up and you could see the satellite, it would look as if it was never moving. It'd move against the background of other stars, but it's sort of hovering always over the same place, you. Every nation has a bunch of these. So the United States has two, one at 75 degrees longitude, one at 135. There's one over Europe, Africa, India, Japan has one covering their area in the Western Pacific. So the entire Earth is covered by geostationary satellites. The scan strategy is they just sort of start at the top and they go back and forth, back and forth, back and forth, back and forth till they get to the bottom. Then they whip back to the top and go back and forth, back and forth. They can control it so that they can do smaller areas more quickly. And we'll see some examples of that. And the other important thing to note, and this will lead directly into resolution, is how big this spot is. Now, this is obviously exaggerated, so you can actually, sort of see what it's doing. If you're looking straight down at the equator, that spot's going to be smaller. As you go further north, because of the curvature of the Earth, it gets stretched out. So like if you took this and you looked up here, this line is going to be down here somewhere, and this is going to be up here, and it's going to be much larger. So the main thing about geostationary satellites is they can take a picture of the entire Earth quite rapidly, 10 minutes for the entire Earth, as we'll see in another slide. But resolution drops off as you get further north. So they're really great for mid-latitudes, not as great for the high latitudes. And we'll see examples of the resolution, and I'll give you the numbers of exactly what it means. Now, when I say resolution, I say there's a spot on Earth. So this is looking down, and resolution is referring to how small an area can you see. So at the subpoint, looking straight down for an infrared channel, we'll get to see what that means. It's about a 2 kilometer by 2 kilometer square. It's not actually square, but I'm going to make it square because it's easier for me to work out numbers in my head. So 4 kilometers squared means everything within that 4 kilometer squared box gets mushed together into one signal that you sitting on top of the satellite could see. It could be trees, it could be water, lakes, clouds, trucker convoys, it could be anything, but you only see one signal. And so, like I said, a box at the equator for an infrared is like 4 kilometers squared. It's like 10 times worth on each side of the box. So instead of being 2 by 2, it's 20 by 20. So like a 400 kilometer squared box in the north. That's why the resolution goes down so much. The instrument name that we're going to be talking about is the Advanced Baseline Imager, ABI. I just throw it there in case, you know, you ever see that name and wonder what it is. Imager means it's a bunch of wavelengths between visible and infrared, and that's what we use. There's other sensors aboard every satellite. They're far too expensive to send up there just for one thing. So it's got other stuff for looking at the sun. It's looking for ultraviolet, so ozone. Over here, there's actually one that looks at lightning from space, mostly for the States, United States, not as much for Canada, but also it's other stuff. But anyway, this is the one we're going to be talking about. So I mentioned there's one over 135 degrees longitude, that's in the west, and one over 75 in the east. And I mentioned the resolution gets worse as you go north, and these two figures show you how much worse in these bands. So let's look at goes west and over Alberta. So if you're over much of Alberta, it's about 2 to 3 times worse than it is at the satellite subpoint, which is at the equator, 0 degrees longitude, or latitude, sorry. So like I said, if you were looking at a 1 kilometer by 1 kilometer box at resolution at the equator over Alberta, it's sort of like 2 to 3. So if we choose 3, it's a 3 by 3, almost 10 kilometers squared box, 9. And I said, everything within that box gets mooshed together into one signal. And that's like the key part of this section, is to realize that. Because it has major implications of your interpretation of what you're seeing from that one little signal from a potentially huge box. So what are the resolutions on board this satellite? And I say we'll be talking what these things mean infrared if you don't know already. There's one channel, which is 0.64 microns, which is straight in the middle of your eyeball, 0.5 kilometer per pixel at the equator. There's a whole bunch of other visible channels at slightly different wavelengths, and they all have a purpose, that are 1 kilometer. And then all the infrared channels, which you can use to get temperature from, 2 kilometers per pixel. I was just thinking in my head just before starting the presentation, you know, like, is this impressive? You know, you're so used to seeing Google imagery where, you know, you have like 5 meter resolution or 2 meter resolution from a few hundred kilometers out in space. But to me, this is incredibly impressive that you can get 500 meters from 36,000 kilometers away. When you think about radiation drops off as r squared, not just r being the distance away, that's actually more impressive than a Google image from a few hundred kilometers away at 2 meters to me. So when you look at the full Earth, the full Earth top to bottom at 0.5 kilometer per pixel in width and height, that's a lot of pixels. Most places who use image operationally will not give you this image for the entire full Earth. It's a huge image. You know, they may store it on a data file for you to download, but to like try and animate 6 hours worth of imagery for the full Earth with this kind of resolution, and it's just too much computer resources. So it gets dumbed down. So I put this down just for interest to the Meteorological Service of Canada, so Environment Canada, where you may or may not get imagery from. They make 3 sectors. They make a huge sector that covers North America, so it's a cut out of the full Earth. And it's just 2 times whatever the subpoint is. So the infrared imagery is actually dumbed down to, at best, at the equator, 4 by 4, but it's never at the equator, so you know, it gets cut off somewhere near Florida type of thing. I mentioned in my little blurby there at the very beginning that they can make sort of smaller areas more often. So CONUS is for the continental United States or contiguous United States or coterminous United States. I've seen it all three ways, basically the lower 48, all the states that are stuck together, meaning not Alaska or Hawaii. We map it to 1.5 in MSC. And then there's these little tiny regions, which I'm going to go to another slide. It's the actual resolution. So as I said, 0.5 kilometers, but a smaller area can handle that. So there's what a full disk looks like. As I mentioned, the resolution gets worse as you go north. Everything gets squooshed together. Those of you who are clever may catch the fact that this is neither at 135 or not at 75 either. It's at 90. And that's just, this is an old image when they first sent up the satellite and it was parked at 90 degrees longitude while it was being tested out. Those of you who have keen eyesight notice a little ball of light in the middle here, wondering what the heck is this thing doing in the middle of the ocean? What could that possibly be? As we're going to see as we go through a little bit of satellite interpretation, this is an example of sun glint, where it's sort of a calm ocean. You have the sun in one location, it's reflecting off the water and reflecting directly into the satellite. Angle of incidence equals angle of reflection, and you get a nice little higher area reflection. And I say that when we'll do a little bit of interpretation, these are the type of things you have to be aware of: is sun, target, satellite, geometry. That's it. We'll see an example of that. So for MSC, Meteorological Service of Canada, if you're ever looking on the website or you're getting imagery from Environment Canada, and it's not sort of like specialized for you, there's going to be something that covers North and North America. Again, these are some a bit older. There's one for the east and one for the west now, so it goes further west, but it looks like this. And that's every 10 minutes. So that's the big value of the GOES satellite. You get imagery often. So if you're looking for the evolution of features, nothing better than an animation sequence with that kind of temporal consistency. As I say, the states are interested in themselves, so they make another sector available that's mostly over in North America. Again, there's one to the east and the west, so this actually punches out to about this longitude way out here. But it's over the water, and there's not too many forest fires over the water, so hopefully, until the big oil spill, I guess. So we don't have to worry about that, but that's every 5 minutes. And then they have these little movable areas. So this is fixed, this guy. These ones, they can move anywhere they want and every minute. In fact, it could be often as every 30 seconds because there's 2 per satellite, goes east, goes west. As I mentioned, there's 2 for the United States. And they can do 1 every 30 seconds or 2 every minute. And this actually has moved over Canada at times. During the Fort McMurray fires, they did actually put this sector right over Alberta. It's not often it happens, but it does happen. The only problem will be, unless things have changed in the last year, Environment Canada to publish that kind of stuff. So you may have to go hunting on the web if you're interested in it. So I'm going to stop there just to see if there was any pertinent questions. I'll sort of pause in my head about the same amount of time when I pick up the phone and there's no answer and I realize it's a robo phone call and I hang up quickly.
Hey, Ron.
Yep.
We do have a question from Piyush at CFS.
Yep.
He'd like to know if you can clarify if the 5-minute domain is the dashed outline or the solid outline in the previous slide, this slide now.
Yep. Yeah, I should have just gotten rid of the dashed line. It is the curved line here. It's just to explain the confusion. It's based on a lat long projection. That's the actual data. So it just cuts out areas based on the latitude of the Earth and the longitude. So it's square in a geographic projection. But it's being projected here. The type of geographic projection you're seeing on your screen is a polar stereographic. And so there's this, have to make a square for the polar stereographic. So this is sort of like dead space in the polar stereographic projection. That's there. But the actual data within this square box for this projection is this line here. So yeah, it covers into southern Canada, but not a huge amount. So it's good for southern Ontario. It's good for, Maritimes. For anywhere in the west where the border's at 50, it's just kind of cuts a little bit. Good question. I said I should have just deleted this dotted line, but That's what happens when you take old slides from old presentations because you're too lazy to redo. Okay, the other type of I'm going to mention one more thing back here. The way we receive data is there's a processing station in Wallops, West Virginia. All the data from the GOES satellite goes down to Wallops, West Virginia. I think it's West Virginia, maybe Virginia. They do some processing. They send it back to the satellite, back out at 35,000 kilometers away. And then the receiving stations, of which there's in Vancouver and Montreal, can receive the data, and then they process it and send it out to all the operational stations. And that's the way it works. So if you have a down link station, you are not getting it direct from the satellite raw. It's getting processed back to the satellite in some processed form, image navigation, that kind of stuff, calibration, and then you receive it. So that was the geostationary satellites. The next type is called the polling orbiting environmental satellites. And what they do, there'll be an animation on the next slide, but I'm going to go through it verbally first. They rotate the Earth going almost over the pole, not quite, and the Earth rotates underneath them east-west as they're going north-south. So you get these long, narrow strips of data. They're closer to the Earth, about 850 kilometers away, so they're much closer to the ground. The good thing about that, and we'll see when we talk about their resolution, is higher resolution in the infrared channels. Stepping back, the reason that the infrared channels have a lower resolution in the GOES satellites is the sun is a pretty powerful radiator, lots of energy. The Earth radiates much less energy at a much lower temperature, so you need a bigger collector to get reasonable resolution. So on board the GOES, the infrared resolution is just naturally lower. These guys are only about 850 kilometers away, so you can get good resolution in all the channels, because to say radiation spreads out at r squared, but you're closer, so you can get more of it. Anyway, so you build up these patches as the Earth is rotating underneath, and you can see, because they're going almost over the equator, you get a lot of repeat coverage from a single satellite up north, and less so over the equator. Sun synchronous just means it passes over the equator at the same local time each day. So if it passed over the equator here at 12 noon, and the Earth rotated underneath the satellite, it's still 12 noon. 12 noon, 12 noon, 12 noon. They have two operational satellites. One is operated by the Europeans, called METOP. Meteorological something something operational, whatever program, FIFA program. And the United States carries the afternoon one. So there's two operational, one in the morning, one in the evening. Unlike the GOES satellites, which are super expensive, they're all expensive, but those are super expensive. They last for decades. These are sort of lifetime is expected for 2 years. So they just throw up another one every 2 years before it breaks, but they usually don't actually break for closer to like 5 to 10 years. Some of them are older than that. So there's a lot of these guys flying up around there. Unlike the GOES, these are direct line of sight. So if you're sitting here, as long as you can see the satellite at your ground station, you can get data. So like this guy could probably pick the satellite up when it comes here, and then he's going to lose it about here because it's going to go the curvature of the Earth. This means it's below the horizon. So even though there may be like about 5, 10 of these guys flying around at any one time, 2 of them operational, a bunch old, at a single site, there's going to be a lot of overlap. So you may only track 5 or 6 of them, but it means you do get a lot better coverage than you might think with just one satellite. So that one, again, it's got all sorts of sensors. The one we care about is the visible infrared imaging radiometer suite, which is in board this NPP. On board METOP, there's something called the Advanced Very High Resolution Radiometer, AVHRR, which is an older instrument and has fewer channels, but we'll talk about that later. And we'll also just mention these other instruments in a slide or two. So just to bang home what I already said, this is what it looks like. I hope it animates properly on your screen. There's the satellite going almost over the equator as the Earth is rotating underneath it, and you can see the coverage from one to the other. There's some overlap. So like in Alberta, you'd see sort of like Eastern Alberta in one shot, Central Alberta, and then the next one, third one, you might see Western. But if you're over the pole, if you're in the north, you get great resolution, great coverage, I should say, temporal coverage. So this is a single pose orbit with some fancy colors, just to whet your appetite for my second to last slide. Say about 850 kilometers in space, about 102 minutes per orbit repeat time. Earth shifts 25 degrees from orbit to orbit. So in this case, you know, from Edmonton, which is where the receiving station is, in this case, there's one up in Resolute and there's one out in Gander. We can sort of pick it up down around Texas and we lose it. Depending on the pass, this cuts off a bit early, but we can go just around to about the North Pole from Edmonton. And I say from Resolute, though, they can cover all the way down to northern Alberta, so they cover off the north. So long and skinny. But if you put a bunch of them together, so this is a bunch of passes all put together with a little box around them, color-coded by how long ago it was from the current time, you can see you have fairly good geographical coverage. It's just that from interpretation part, it's a little harder because this image might be 2 minutes ago, and this image down here, a little corner, could be 5 hours ago, and this one could be 3 hours ago. So it's not like GOES. You can't just animate it and get this fluid 10-minute. You know, some periods in the afternoon, you might get 3 satellites in the space of half an hour. And then overnight, you only might get 1 in 6 hours. So not as good. But the difference is, as we say, we're looking at resolution, because these are lower to the ground, no worse than 1 kilometer per pixel for all channels. So even at all latitudes, because if you remember, this guy is spinning around looking down. Now, it's not exactly 1 kilometer because it's looking, the way they work is they look across the Earth, then they look to outer space, and that's to get a temperature patch from outer space, which is then used to calibrate temperatures. And then as it's flying north, it spins around, spins around. So even over the far north, it's still looking straight down. So it's 1 kilometer when it's looking straight down. Because of the curvature of the Earth, it's actually closer to 4 kilometers on the wing. So it's 1 kilometer in each scan line going up, but it becomes like a rectangular box 1 by 4 at the wings. But it's still like 1.5 way out to about here. So I'm just going to use 1 by 1 because it's, again, an easier number. So they have great resolution even over the north. So like I said, the GOES satellite might be a box 100 by 100 kilometers squared. This is going to be 1 by 100, so 100 times better in the north. Depending on the satellite, you can go higher. The VIIRS can go as high as 400 meters per pixel, and MODIS, which is another satellite we didn't talk about, it's a more environmental monitoring research satellite, but it's still used for weather forecasting. And it has a couple of visible channels go as high as 250 meters per pixel. So what else is on board? Just to give you a little bit of background. We talked about these imagers receive radiation from visible and infrared wavelengths. Sounders may use visible and infrared as well, like this one, the infrared sounder uses infrared. There's a microwave sounder which uses microwave, and microwave can see through clouds and can detect precipitation. And the sounders are used to get vertical soundings of temperature and moisture. Same thing as when you send up a balloon with a temperature and moisture sensor. But this can be done from space with some fancy processing. It's not as accurate, and I'm not going to mention any more than that. It's a bit off topic. Microwave is also good to determine surface features because the Earth radiates naturally, passively, in the microwave as well. And it does so differently depending if there's a lot of moisture in the soil or if it's covered with snow. If you have winds in the ocean and you get a little bit of froth in the waves, little capillary waves, depending on how many capillary waves, it changes the microwave emissions. So you can use microwaves to do all these surface features as well, but it's pretty low resolution. but it's still useful because, you know, if you're looking at covering how much snow in the north and you just want some broad brush, even if you're just getting it by 50 kilometers, that's good enough. Then there's other things we're looking at. I mentioned, you know, like for space, ozone, lightning. When I say not yet proven useful for Canada, that's only because I say it doesn't really go much into northern Canada. It's lower resolution where it does do it. And it is useful. It's just that it may not be a lot more useful than the ground-based network. So it's a question of cost of, you know, doing it and distributing the data, collecting it. I mean, the data's there versus just using what you got. Anyway, all of these sensors that I mentioned are using passive radiation, i.e. they are not beaming out their own radiation, they're just getting whatever is being sent to them. There's another type of instruments, which are active instruments, which just like when you look at radar on Earth for precipitation and thunderstorms, they do this from space. These are all similarly low Earth orbits, like the POES, because again, the radiation is spreading out as r squared. If you're too far away, it's going to be pretty weak when you send it to the Earth and it gets bounced back to you, and that's r squared each direction. So these are all fairly low Earth orbits. Like I said, same 850 kilometers. RadarSat, which is good for high resolution image ice, ice types. From the fire point of view, I've seen things where they use it for burn scars. You can look at the same idea. You can beam microwaves onto the ocean and get returned radiation to do ocean winds. And you can even look at the vertical profile, same as you do with radar on Earth, looking at thunderstorms. You can do the same thing with large systems, hurricanes. This is probably a hurricane profile in the vertical from space. So it's pretty neat. Operationally, not as useful in terms of evolving systems, because as you can see, these are long and skinny and not much overlap. So you'll see this, and then you may only get one area a few times per day. So if you're trying to figure out where a forest fire is going, is one image every 6 hours, maybe, one every 2 days, maybe useful, depending upon the instrument. So they're interesting, but they may not be applicable to you. So any questions about the polar orbit before I show you a few pictures of what resolution differences look like between these satellites and geographical area? 5, 4, 3, 2, 1. Hang up before the robot answers. Good, done. So this again is an older slide, but it shows a long skinny POES pass and a geostationary orbit pass. And up north, where you're sort of like probably 5 times worse compared to the sub point for the GOES satellite. So an infrared box, instead of being 4 by 4 in this older satellite, it's like 20 by 20. So 400 square kilometers per pixel. One is a blurry mess. One you can actually see what's going on. In the newer satellite, here's the best we can do, 0.6 microns at 1 kilometer operationally. Like I said, you can actually do better than this. This is the GOES image. And this is a POES image for almost the same time. It's not the same, but it's close. And you can say, well, that's not so bad. And you're right, it's not so bad. It's actually quite useful. When we move to the infrared, where I said it's lower resolution, it's like 2 by 2 at the equator and up here at the pole at the 70 north. If you're not sure where we are, this is northern Quebec and this is southern Baffin Island. So this is, instead of, like I said, 2 by 2, and we only use half of that. So it's 4 by 4, 10 times worth, 40 by 40. It's a blurry mess. So here where you think this is a solid cloud deck, if we look at it in a POES satellite, you can really see what's going on. And this is where I say, you only get one signal per box. So down in this area, up in this area, you're seeing a combination that you riding along with the satellite of cloud and ground. Ground could be land, it could be ice, it could be water, which will all have different properties. You get one signal. So in this case, it looks like a solid cloud deck, but in fact, it's nothing but that. And the other thing, I don't have a slide for it, but I'm going to just sort of wave my mouse on the screen when I explain this. You'll notice when I go to the GOES, how the higher cloud seems to be quite far north. And there's an issue called parallax. And I say, I don't have a slide for it, but just look at my mouse. Pretend this is the Earth. This is south, this is north. And you have a cloud sitting right here up north, and it's pretty tall. So it goes up to this, well, let's say it goes up to about here somewhere. And the geostationary satellites is over here, way to the south of the equator, looking at it. So it's looking down, down, down. It sees the top of the cloud here, and it projects it to think it's way too far north. So in the north, that's many tens of kilometers. Over Alberta, it's like a couple of pixels worth, so maybe 5 to 10 kilometers for a thunderstorm. So if you're looking on a GOES image and you're looking at the top of a thunderstorm, it will often appear to be about, let's say, 5-ish, 10 kilometers north of where it actually is on the ground because of this parallax issue. You don't have that with the pose because, again, the pose is looking straight down as it's moving in a north-south direction, sweeping east-west scan line. Okay, as far as resolution, like I said, a meteorologist at best is using about a 1 kilometer per pixel resolution. And if you zoom in the lower mainland, southern Vancouver Island, this is what it looks like. Pretty good if you were just broad brushing things, but not as good as 250 meters, where now you can actually start to see landscape features like the Fraser River and deltas and islands. So, you know, sometimes people are so used to Google images, they sort of phone up the weather office and say, well, do you have an image that shows, you know, some feature like a bit of fog that was coming up some inlet? And the answer is probably not, unless you're lucky, right? It's just not the way it is. And where I can sort of show you that more is this one. This is the Mount Olympus, the Olympic National Park in the States, just north Seattle. It's down here, so south of Vancouver Island. Here you actually can see fog leaping up and coming up the valleys. So just show you the resolution is a major feature. And if nothing else, I say from this sort of section, try and keep in mind and say to yourself, okay, I'm a satellite traveling out in space. I'm looking at this latitude on a GOES image. Based on what he showed me, the resolution of this box is approximately 5 kilometers by 5 kilometers, whatever you think it is. So there could be a lot of stuff inside this box. I get one signal, whatever it is. So I have to use my smarts in saying, am I looking at the ground? Is there likely some clouds? Because I looked at I'm looking up at the sky and I can see that there's cumulus clouds, so it's cloudy. What am I likely seeing? Okay, I'm going to move on to the next station, next part, but I'll wait 5. And while I'm waiting 5, I'm just going to run and get my wristwatch so I know my own time. I don't go over. We're good. I'm back.
Hey, Ron, I do have a question from your last section.
Yep.
Jarrett would like to know, could the CloudSat be used to look at the vertical plume of a large plume-dominated fire, or is it too small of a scale?
Way too small a scale. And if it did, you would be lucky because I say you're only going to get that instrument. It's more geared towards tropical. I think I'm not even sure it's in a polar orbiter if CloudSat's in a more east-west. So let's pretend it was anyway, even if it wasn't in a north-south. That's a very narrow looking instrument. So you'll get a repeat over one area. Could be every couple of days in the north type of thing. So even if it could get it, I think it would be way too small scale a feature to map properly. And you'd only see it once. So like I said, that instrument is a research instrument, not sort of an operational instrument. So yeah, that's what I mean. There's all this neat stuff out there, but it's not necessarily all operationally useful. But it's still neat stuff, for sure. Okay, so I mentioned there's different wavelengths, which I call channels because that's what they're called. It's just like channel 1, channel 2, channel 3. And there's documents out there that tell you what channel is what wavelength. And these vertical lines here are some of the GOES wavelengths from what your eyeball sees all the way to long wave, which are sort of like infrared cameras, which show you heat signatures. That's what all this stuff is, and everything in between. These are the channels on the GOES satellite, 16 of them. And you can see where I took this one from. And there's something saying, what are all these used for? And we're going to go over some of them, not all. Some visible channels, some, 0.8, like why 0.85 microns? Like, what's the deal there? And, if you're around 6 microns, 7, why? Why those? Why not 2.2? Oh, there is one at 2.2. Why that? That's what we're going to go through. If we look at the ones on VIIRS, you'll notice some are the same, like 0.865. 0.865. Why? These things cost a fortune to send up. Nobody's going to send up one of these satellites and spend the money in developing a filter and a wavelength without justifying it to the hilt as to it being useful. So you can imagine that every single one of these serves a purpose. So I'm not going to go over all of them. I'll go through the ones that are more appropriate to you. But they all exist and they're all important. Here you'll notice 750 meters. We dumb it down to 1 kilometer operationally. I said 400 meters, it's actually 375. And you'll say, well, these are kind of like repeats. Why is this one here and this one here? Why have I got a 0.865 and a 0.865? I had mentioned earlier that the VIIRS is like a newer satellite, and then the Europeans carry METOP as the morning satellite with an older instrument. These down here are the wavelengths of the older instrument. So it carries on that heritage, which is really important when you're trying to do long-term climate studies and you want to know what's happening over decades. If you suddenly start using a completely new frequency, even if the wavelength, because they're never discrete, they're always a wavelength range. If you change the wavelength range, you change the response. So you're going to suddenly bias your long-term studies. So they maintain the same wavelengths. And then there's this really cool one called the day-night band, which is visible. You'll notice it has a really wide wavelength range, and it works with moonlight. If you have a quarter moon, that's enough radiation, visible radiation, to see clouds in the ground. And will be one example of that towards the end, how it approaches, or how it's used for smoke, which is only if you're lucky. So the question is, why so many? What do they all do? And that's what we're going to go through in this next section. And for that, like I say, we really have to know something about the atmosphere. So here's the sort of simple picture. Here's the sun sending radiation to the ground. It peaks at about 0.5 microns, and by no mean feat of evolution, your eyeball sort of is sensitive to that range. It's relatively narrow, but very intense. If there were no clouds and the atmosphere was clean of everything that might absorb or scatter radiation, it would all get absorbed by the Earth. And then the Earth would re-radiate it at a much lower temperature, peaking around 11 microns, but really over a range from 3.5 up to almost 20. The sun's temperature is around 6,000 degrees Kelvin, which is, Kelvin is like 273, Celsius plus 273. So if it's Earth radiation, I'm going to say it's like 300 degrees Kelvin. So that's like 23 degrees Celsius on average. If this was a really to scale diagram, and I don't know that it is, the area under the curve here would equal the area under the curve here, because if it wasn't, what would that mean? It would mean the Earth is either going to heat up nonstop or it's going to cool down nonstop. This is climate change aside, of course. Now, in fact, there is things in the way. Some incoming solar radiation will get reflected by clouds. Some will get, if there's snow on the ground, will be reflected by the snow, so it won't get absorbed into the ground. Some of the radiation leaving the Earth will get absorbed by clouds, and then the clouds will absorb it and then radiate it back out to space to you on the satellite. It could be that there's atmospheric gases or particulate matter, like volcanic ash, that will absorb the radiation. And going back to the solar, if there's smoke, that will obviously scatter radiation, won't make it to the ground. So there's a lot of things going on there. I did say though, oh, the sun's temperature is around 6,000 degrees Kelvin. How do I know that? I didn't take a thermometer up there. Well, when you have radiation and it follows this curve, this is sort of a mathematically derived curve based upon this particular, what should I call it? Not theory, I'll call it whatever you want. Statement. You have black body radiators, something which absorbs all the radiation and incidence upon it and then re-emits it all is a black body. This is actually wavelength dependent, but we'll leave that aside for now. So if I receive a bunch of radiation at a particular wavelength and then I re-emit it, even at a lower temperature, I'm a black body. And if I am, I can go radiation is proportional to temperature to the 4th power. So I measure this from the satellite and I can calculate this from this relationship. A lot of things on Earth are close to black bodies. The Earth's surface, say if there's snow, no, because it's going to reflect the clouds or the radiation from the sun. Thick clouds, yes. Thin clouds, not. If it's a thin cloud, some of the radiation will pass from the ground, will pass right through the cloud to you on the satellite. Some portion of it will be absorbed by the cloud and then re-emitted at the temperature that the cloud is at. So if it's a cirrus cloud sitting at 30,000 feet at -40, you're going to get a radiation that is consistent with a temperature of -40. So again, when you're sort of thinking about resolution and all these things, I'm getting one signal and I can calculate a temperature. Well, is it meaningful? No, because it's not of one object. It's a bunch of different objects. If I'm looking at thin cloud and I get a temperature and I want to go to a tephogram and say, oh, well, I've got this sounding of height versus temperature. Can I use it if I think it's thin clouds? No, you'll get a wrong answer. The radiation you measure from the satellite will have ground temperatures in there as well. So you'll end up with a temperature that's too warm and you'll assign the height that's too close to the ground. But for now, let's stick with this. So like I said, not all radiation from the sun makes it to Earth. You can get scattering by smoke and clouds. You can even get some absorption, as we'll see. And not all radiation from Earth makes it to outer space. There are various gases in the atmosphere, thankfully, like water vapor, or we'd all be dead. And they might absorb radiation depending upon the wavelength. Some will pass right through, some will get absorbed. And there's other things other than just atmospheric gases. There could be particles, like I mentioned, volcanic ash, particulate matter, whatever you got. So this is just showing not to scale the radiation coming from the sun, mostly around 1 micron, like I said, peaks in the visible. And this is outgoing radiation from the Earth, peaking around 11. The reason it doesn't look as flat as the previous picture, the other picture went to like 20 microns and this one goes to 70. This second one is showing you where the channels are on the GOES satellite with respect to absorption. So some channels, like, these ones, are where there's very little absorption by the atmosphere. They're purposely placed there. These ones are purposely placed where there's huge amount of absorption in the atmosphere. And that's the type of stuff we're going to look at in the next few slides. Is this, why is a wavelength chosen with respect to the absorption and scattering? So while we're going to concentrate mostly on wavelengths, there are other things that are part of the details that are important. such as what is the scattering and reflecting material or the absorbing material. For solar radiation, it's mostly scattering, reflecting. There's only a few absorbers. But what's the particle size? Depending upon the wavelength and the size of the particle, you can have different scattering mechanisms. What's the shape? What's the sun angle? So on this next slide, I'm going to show you something that is similar in concept to that early slide where I said sun glint, where you saw that little ball of lightness on the ocean. This is going to be another more applicable example of the exact same thing. So this is from the GOES East satellite. So the satellite's over here. This animation is going later in the day. So the sun's over here. And you can see this area of smoke coming down the coast. As it's coming down, it looks like it's getting brighter. And you might say to yourself, oh, well, it's getting thicker. Probably not. It's more that clouds and smoke scatter preferentially in the forward direction rather than the backwards direction. So as the sun is moving this way, you're getting more forwarding scattering off the target, smoke, onto the satellite over here. And you can see the exact same thing happening later on over the clouds. So it looks as if these clouds are getting brighter, and you might say, oh, are they getting thicker or whatever? No, it's just the sun's satellite target geometry. So in general, smoke is easier to see when you have the sun low in the sky, and though it happens both ways, from the satellite that's on the opposite side of the Earth than the sun. If you were looking on opposed satellite imagery, you can sort of think of it the same way. If the satellite is, the satellite's going up the center of the Earth, but it's looking east-west. So if you had the sun over here and the satellite coming up this way and the smoke was over there, you'd have the same thing. You'd have sun, target, opposed satellite going up this way. And as, so it may be on one satellite orbit for opposed satellite, you have that geometry, but then I say the Earth rotates underneath the satellite. So the sun satellite target is different, and suddenly the smoke isn't there anymore, simply because the geometry has changed. So again, these are the kind of things you have to be aware of. It's not just wavelength, it's other things as well. But I didn't want to make it sound like, oh, if the sun is overhead, you'll never see smoke because you don't have this preferential scattering. If you have, this is like 22, so this is in the summer. So the sun's close to overhead. It's not, it's to the west, but close. You'll see smoke all day if you have enough smoke. And this one is obviously a spectacular example, but it's there. Now, one thing I'll mention, because it leads into our very first set of slides. 0.4 microns. So that is one of the shorter wavelengths, often assigned called the blue, because it's in the blue color of the visible spectrum. So we're going to concentrate on wavelengths. We're going to start with the solar wavelengths. I'll make my next pause after this section on solar wavelengths. I should say visible wavelengths, because I say it could be from the moon as well. So 0.47 blue is one of the wavelengths. 0.64 is one you most often see because it has the highest resolution natively, and it's where your eyeball is kind of most evolved to. So that's one you often see when you just go to a website. If they're going to show you one visible channel, it's often the 0.64. But shorter wavelengths scatter more light, which means if you have faint smoke, which I'm hoping you have monitors good enough to see this faint smoke, you can see it at 0.47, where you won't see it at 0.64. So it's an extremely valuable channel on any sort of recipe that is used from GOES satellites that is used for smoke detection. Because I say there's more scattering, makes it easier to see. Like I said, though, you often just, if you're just looking vaguely on the web and you say, oh, just show me a visible channel, you'll have to watch out, because this is the one you'll more likely see, because that's kind of the historical one that's been around for decades and decades. Often Wavelengths are put together to make color imagery. This is a true color imagery where you just put 3 together, red, green, and blue to make a true color image. And like I say, the blue channel, the 0.47 microns, is usually assigned to the blue color gun. And that tends to give smoke a kind of grayish, bluish tinge. It can be brownish as well, kind of depends what particles are there, because some will scatter more in the red, depending upon the particle size. If you're not used to looking at smoke on satellite imagery, you probably all are. You can sort of see, yeah, smoke just looks different. It's more diffuse than clouds, which tend to be brighter and have, you know, harsher edges. So it's pretty obvious what you're looking at once you know what you're looking at. Okay, that one's fairly straightforward. This one, not a lot of people look at the 0.865 channel. Like I said, that's on almost every satellite. Why is that there? Okay, this picture is showing you 2 things. It's showing you the albedo or the reflectance, which is basically how much radiation is reflected divided by how much is received. So if it's all reflected, it's 1. If none's reflected, it's 0. Snow, for example, is pretty bright, 80% reflected, but it sort of drops off slowly with increasing wavelength. Like you say, your eyeball cuts out around here somewhere, right about there. Vegetation, on the other hand, if you look at it at 0.5, 0.6, vegetation looks pretty dark. But a lot of vegetation right around 0.7 suddenly gets much brighter, reflects much more solar radiation. Why? I couldn't tell you. I don't know the physics. But it has really important properties for looking at the ground. Good land-water contrast. Why do I say that? I'm going to give you another reason why we use it as well. So if you're looking at lakes, lakes tend to be dark in 0.865 and at 0.65. So water's dark on either side. However, if you got a vegetated surface around those lakes, on this channel, the land looks quite bright against the dark lakes, and it's much easier to see ground features. Much, much easier. Just as an aside, the other reason this channel is so important, it's used for measuring health of crops. Like this is used worldwide as it's called the Vegetative Index, where they do a differencing between imagery at 0.865 and imagery at 0.6. And they say, well, if it's much brighter at 0.865 than 0.6, the crops are healthy. But if they're almost the same, that means the crops obviously haven't grown much and crops are having trouble. So it has things other than just meteorological. But from the weather side, it's quite important, and it gives you these good ground features. So here we are at 0.47, the one we said looks good for smoke. Here we are at 0.64, the one you normally see because your eyeball's tuned to it. And here at 0.86, where the vegetated surfaces are much brighter. And now suddenly we can see all these small lakes. Good ground feature discrimination. And that alone makes it a very, very useful channel. Okay, another channel, which I wasn't going to do, but I have one example with smoke, so I will. I said there aren't a lot of absorbers of solar radiation versus outgoing long-wave radiation, but in fact, water vapor in the atmosphere as a gas does absorb around 1.4 microns. And there is a channel put there. It's not to detect smoke. Now, when I say water vapor absorbs, most of the water vapor in the atmosphere is near the surface, not much up above. So if you have some radiation leaving the ground, it gets absorbed here. If you have sunlight coming in, most of it passes through, will hit the clouds that are up here and get bounced off. If there's cumulus clouds, the radiation will come low in the atmosphere where there's lots of water vapor. That'll just get absorbed and you won't see it, you being on the satellite out in space. So it's really good for detecting just high, thin cloud versus lower cumulus cloud. And you say, well, who the hell cares about that? Important for climate studies. Even thin cirrus, which is hard to detect, makes a big difference on the radiation budget of the Earth. So climate modelers and people doing short-term incoming solar radiation, outgoing long wave radiation, budget experiments, they care. The nice thing from your point, and I guess military cares because you can see contrails. What you might care is though, sometimes you can see smoke. So I just happen to have this one example. So here's the 0.4 blue, I said, which was the best one, 18 GMT, the best time. And so this is when the sun's overhead. You don't see anything here. But here you can actually see a plume of smoke along the coast. And you'll notice, this low cloud over the water, you don't really see it. It's there, but not much. The cirrus still shows up, like I mentioned, there's not much water vapor high up in the atmosphere. So there's nothing to absorb the solar radiation. So it's being scattered, reflected off the high cloud. But that solar radiation is not making it down at this wavelength to the ground because the water vapor, this just above these clouds, is mostly absorbing it. So like I say, interesting channel. There are websites that show all the channels from the GOES satellites. So you might have fun looking at this one just to see if you can see smoke when you know smoke's around. But based upon what I've seen, just casual looking in the past, it's not always there visible. Next one in the ones we like. This is probably a more meteorological, useful, but I still think it's a cool one. We said even between 0.5 and 1, we could see snow dropping off slowly, but then it falls like a rock down to about 1.5, and here's a channel at 1.6. Why do we care? Well, I'll tell you now that water clouds, not snow or ice clouds, are still pretty bright at 1.6. Their albedo is pretty high. So the problem is if you're trying to look at a white cloud over a white snow surface at these wavelengths, it's white on white, it's really hard to see. But here you'll be looking at a white cloud on a not very reflective surface at 1.6. So suddenly white on white, hard to see, but at 1.6, suddenly this low cloud or fog is easy to spot. So for meteorologists, it's an incredibly important channel for trying to pick out low cloud and fog. If you're a pilot, also an incredibly useful channel for picking out low cloud and fog over a snow surface. You can see all this is snow, and we know it's snow, not cloud, because we can see, like river valleys in it. They don't look like bits of cloud or breaks in cloud. It looks like ground features. And you can see here, it's quite dark. And if you were listening to me drone on about 5 minutes ago, when I said vegetation gets really light above 0.7, dark light. Why? Because very reflective vegetation, not reflective vegetation. And so you got to sort of get used to look at these things, and then these differences between imagery become quite clear. Another one we're just going to mention, I don't know how useful it would be. Forest fires do emit visible radiation. You can see them. And it turns out they emit more at 2.24 microns than they do at what your eyeball is tuned to, or even lower. So here's a picture at night showing 2.2 of one little spot, 1.6, and then an infrared channel, which we're going to talk about later, where you can see the thermal signature as opposed to the visible signature. It is used in some schemes to detect fires, but I say it's sort of only useful at night when the sun's not around, because the sun will far dominate any response from this channel itself. Okay, so I'm going to do my 10-second pause here before we move on to infrared radiation.
Ron, I have a question myself.
Sure.
Looking back at the snow channels, can you speak briefly to the usefulness for tracking snow cover and snow melt in the spring on the ground?
Yes, it is good for that. No doubt, but it won't tell you the thickness so much, because you'd only need like a light dusting of snow to get a very strong change in albedo. So it's a bit tricky in that response. There is another channel at 1.2 microns. I have a slide, I took it out, where it is actually sensitive to snow grain size. So when snow first falls and it hits the ground, this is supposed to be a fire thing, not a snow thing. But anyway, when the snow first falls, the snow grains are quite small. And even if it's big, even if it's like large snow crystals, it's still relatively small. And as the snow metamorphoses, it sort of melts, it gloms on with other crystals, and snow grains grow to a much larger size. And at 1.2, let me go back here. So you can see here in this region that's falling quite quickly, right? So there's a channel around here in this sort of descent part, which is sensitive to snow grain size. And as the snow grains get bigger, the reflectivity, I think it goes down. I can't remember if it goes down or up, but it changes a lot with snow grain size. And so that one you actually can use a bit better for looking at the age of the snowpack, because fresh snow looks different than old snow. Whereas at 1.6, it's kind of, like I say, you don't really have that variation with snow grain size. It's not as sensitive to that. So I don't know if that answers your question or not. Like I said, you're going to get in trouble in that small dustings of snow make a big difference. So if you're kind of keeping track of if it snowed recently or not, and then how's it receding, yes. What it has been good for is sometimes do we have ice covered lakes, that kind of thing, with a snow surface around it. So you can sort of see, not that, I'll take that back, because that's actually more for the 0.865 where you can get good land water contrast. Anyway, does that answer your question? I'm going to say it could be hard just because I say it's so reflective with small depths of snow. What you're almost better off is there is the microwave chat products put out by Climate Canada. I don't remember what the official name is. Where the microwave imagery, the passive microwave, is sensitive to the depth of the snow. So they actually put out a snow depth product. So it's very broad brush. Like a pixel is like this big, fairly large. But if you want to monitor snow depth, those are probably better products if you want to broad brush it, say from microwave. Okay, on to the infrared. So again, I said the Earth will absorb whatever radiation is received on it and then re-emit it at a lower temperature. If there's clouds, they're black body radiators, so clouds will absorb it. So say if the Earth is radiating it, it radiates it at 300 degrees Kelvin. That radiation is going out to space, but it gets absorbed by a cloud sitting at 30,000 feet. That's at -40, so the cloud will absorb it and then re-radiate it at a temperature that's relative, to -40. And that's the radiation that the satellite will receive. And you'll say, -40, it's a cloud. But all that depends upon what is doing the absorbing. Oops. And how thick is it? If it's a thin layer, maybe a lot of radiation will just zip right through it. If it's a thick, then it will be a black body and absorb all of it. Is it a gas like water vapor? Is it a solid particle like volcanic ash? How big is that particle? What's its shape? All these things make a difference. We're talking mostly about this one and this one. So here are the three main absorbers, of which we're only going to talk about one of them, though there's channels that are in all three. So I'll mention one of them, the other ones now, just for fun. Water vapor in the atmosphere, very broad, around 6 microns. Now I mentioned most of the water vapor in the atmosphere is close to the ground, and then it diminishes as you go up in space. Around 9 microns, big absorbing channel due to ozone. Ozone is mostly In the upper atmosphere, there is ground-based ozone due to pollution. So you get some absorption up in the atmosphere here, and then CO2 is pretty broadly dispersed vertically, and that's used by the sounder channels to get temperature and moisture in the vertical. So we're going to look at a few of the channels here. 3.5 microns is a little bit of sun and a little bit of solar. So when the sun is out, that kind of dominates. When the sun's not there, it's mostly infrared. It's an interesting channel because it's like the 1.6. There's a big difference in reflectivity if it's water or ice. And going back to what we were talking about, particle size, the reflectivity also changes with particle size. So you can use that to get a little bit of microphysics. So this channel has a lot of different uses because of having a combination of solar and infrared, and this characteristic of having different reflectivity with particle size. For you though, hotspot detection. This is the channel which is used to detect hot areas on the ground. And this is just a animation sequence where the warmer it is, the darker it gets until they change it to yellow, and it's super hot, it turns into red, and you can easily see the hot spot. And that's the visible image with the smoke from those hot spots. So that's its main use for you guys. Now, this is going to say, I've been hammering along, you get one value per box. And this is going to be like, well, what if the pixel is not filling the box? At 3.9 and 10.7, I'm going to start the animation. If you didn't have anything in the box, they'd give you the same temperature. If the fire filled the box, you'd get the same temperature. But while it's growing, the subpixel resolution, you actually get a higher temperature at 3.9 than you do at 10.7, independent about how much of the box it's filling. So even if it's subpixel fire, you can still detect it, and you can detect it better at 3.9. So this is the go-to channel if you're looking at hotspots on the ground. Water vapor. Now I mentioned it's in the absorption channel is around 6 point something. That means water vapor in the atmosphere is absorbing radiation coming from the ground. Now, near to the ground, you're getting a lot of absorption, and so you don't get to see water vapor right at the ground because as it emits vapor a little bit higher, it gets absorbed by water vapor a little bit higher. If you're at the top of the atmosphere, there is no water vapor, very little. So you're not going to see much energy from water vapor radiating high in the atmosphere because there is none. You're getting it through some depth in the middle. So you get these what are called weighting functions. You're going to see them again in another slide. The important point here is you're seeing a depth in the atmosphere, not a single point pressure level. If you're on the wings of this absorption channel, like at 7.3, there's not as much absorption by water vapor, so you get to see lower down in the ground, which is why this green one at 7.3, the weighting channel is lower than these other two, which are more closer to the middle of the weighting channel. So in this little animation, that's what it's trying to show. The animation, which has always worked for me until right now. That's okay. I'm just going to go back and forth here. There we go. So it's just showing this H2O near the surface. It's white saying you never get to see radiation from that level. It's being absorbed by this level. Now there's less here than there is here. So some of it will squeak through. Where there's no water vapor up here, you're not seeing any radiation from that level because there's no water vapor to radiate. It's coming from the water vapor down in this middle level. So you're not seeing any from down here. You're not seeing any radiation from here. You're seeing it from the middle. Now, if there's a cirrus cloud sitting here, let's pretend, it's going to absorb this moisture, radiation, I should say, from the moisture, and re-radiate it as a cloud, and you're going to see it like it's a normal infrared imagery cloud. Eventually, you at the satellite see what's coming out, but the point is you're seeing it from clouds and you're seeing it from water vapor. And the reason it's such an important channel for meteorologists is you get to see movement of synoptic scale features, even if there's no clouds. So I kind of went through this. These are the weighting functions, which are just saying to what depth of the atmosphere. So if you sort of look at the half power point for this red one, you're seeing radiation rising from about 300 and 250 millibars to about 500 millibars. So just when you do look at imagery, keep in mind it's not at one pressure level, it's through some depth. If the atmosphere was dry, there was no moisture, then you get to see to the ground, even in water vapor channel, but that only happens where the air is driest to dry, like the Arctic. And so this is the water vapor channel. I see where you see the bright white, that's just cirrus cloud, top of thunderstorms, whatever. The interesting stuff is this gray stuff where you can actually see ridges and troughs forming and deepening and synoptic scale features rotating. And there may be no upper level cloud at all. There could be low level cloud. We don't get to see that because low level cloud radiation got absorbed by the water vapor in the low levels. So super important. Window channels, that's where there is no absorption, and that's the one that you normally see if they're just showing you infrared imagery. It's good during the day, it's good during the night. No atmospheric absorption except clouds absorbing it and re-emitting it. And that's the one where we assume black body temperatures and we can calculate temperatures, sea surface temperatures, and all that good stuff. Okay, the VIIRS day-night band. It's the visible from moonlight. These are clouds you're seeing in the middle of the night. That's like midnight. And if it's in the right place, you can barely see some smoke. So I wouldn't say you're going to get it all the time, but you'll get it most of the time. So that was the channel thing. I'm just going to quickly, in about 2 minutes worth of time, 3 minutes, finish things off with a few couple of slides, and then we can fill the rest of the time with questions. So you saw a few color imagery. You saw a true color imagery of the entire full disk. When I did the single post pass, it was a color imagery, and I'm just going to talk a little bit about that. So what you do is you combine red, green, and blue color guns of your computer. You assign different wavelengths to those 3 color guns to make a nice, pretty color image, to try and highlight some atmospheric feature or process that you're interested in. Different wavelengths are useful for different things. So instead of having to look at 3 different images, or, I can combine 3 images or more if I do some image math into 1 image, and I can get much more information. At the same time, though, it's got to look pretty. If it looks like a dog's breakfast of colors, your brain will just shut down. Many schemes. There are some looking for air mass, some that say, what's the convective weather? Is it strong? Is it weak? By looking at particles and microphysics, this kind of stuff. Air mass looks at ozone, because ozone intrusion into the atmosphere tells you something about synoptic scale weather. There's ones for volcanic ash that's there. As I mentioned, you get different absorption if there's volcanic ash. It's like the 8.5 micron channel we didn't cover is important for that. There's a bunch of different recipes for fire and smoke. So we're going to look at one of them. But before that, here's the simplest one. Take a red, green, and blue wavelengths, 0.4, 0.5, 0.6. So that's your eyeball, 0.4, 0.5, 0.6. They look all the same. Shove them together, and boom, you get a color image. That looks a lot prettier. And, it's a lot easier to detect ground features from clouds because green is easier to see than against white than sort of dark gray. And if you're looking, you get to see some difference in ocean colors, which tells you something about chlorophyll and what's in water. So as we're going to look at one fire scheme. And I think some of the other lectures that Brian mentioned probably will cover more in more detail. The basics are you have to know at least a teeny tiny bit about what happens when you combine colors. So the primaries of most computers are red, green, and blue. So that's why they're usually done this way. If you stick together red and green, you get yellow. You stick together red and blue, you get what looks like purple, or more correctly magenta. and you stick together blue and green, you get what looks like light blue, or more correctly, cyan. That's kind of the basics. I mean, obviously, if you have a lot of red and just a little bit of green, it's going to be not yellow, it's going to be more pinky or whatever. But let's hold on to at least those sort of 1, 2, 3, 4, 5, 6, 7 colors in our brain. So here's one that's made from the polar orbiting NPP satellite that has the VIIRS imager on board. And we're going to choose the wavelengths that we think are useful for trying to figure out where fire and smoke are. Well, I said, what is the most important channel for hotspot detection? It's 3.7. Well, let's use that. We want to know ground features. Otherwise, it's against this blobby background and we can't tell anything. So let's use the one that gives us good land, water, ground feature discrimination, 0.86. And we want the shortest wavelength we can get that's still useful. And because it's VIIRS, and we're going to use the 0.64. That's the more normal one on VIIRS. If you're trying to use the standard kind of wavelengths that are also on AVHRR. If this was a GOES image, a GOES-based one, they may not use 0.6. They may use something else that's a shorter wavelength. So how does this work? Okay, we're going to say, put the 0.37 on the red gun, because we're just thinking red is bad, red is hot. So hotspots, make them red. That's what our brain expects. Ground features, we're kind of used to green vegetation. So, okay, well, let's say we'll assign the green gun to 0.86. If we did it otherwise and we had green fires and red ground, you'd probably be going, yuck, looks horrible. And then smoke, what color should smoke be? Sort of a grayish, bluish thing? I can deal with that. So we'll do it that way. So what about clouds though? To say they're bright at 0.86 and at 0.64. If they're low level clouds, they're pretty warm, but they're probably not going to be enhanced as red. We'll do a good enhancement so that only really hot things show up. They'll just be kind of dark and they won't contribute. So we'll have clouds mostly just from the visible channels, blue and green, cyan. So this is probably, maybe the start of some pyro CVs, starting right here, where it's cyanish. And this little recipe, which you can see I got from here, visit quick guides, blah, blah, blah. It goes to, it says red 3.7. This is how we're enhancing it. And if there's not much 3.7 mic contribution, what are you looking at? If there's lots, what are you looking at? So we'll just concentrate on this one. Lots of 3.7 radiation. Oh, it must be really hot. Lots of radiation at 0.6 microns. Oh, it must be healthy vegetation. If there's clouds, they'll be bright as well. And 0.64, oh, lots of scattering, smoke, make that blue. So that's how these RGBs work. Incredibly useful. Like I say, instead of having to look at the red separately from the green, separately from the blue, because you look at the red and say, I can see a hotspot, but I have no clue how far it is from Lake Wobegon. Well, when you have the green, you can suddenly see Lake Wobegon and you know how far it is. And the blue, of course, makes sense because you want to see the smoke. So that was one of the things, just say, you don't just use single channels, you use other stuff as well. And my last slide is to say, and you can do other things with satellite pictures. Here's an example where you just track cloud elements visually. By that, I meant a computer looks at radiation returns. And you can do it with IR imagery, visual imagery, water vapor imagery, and you just follow them along every 10 minutes. And from that, you can get trapped winds at different levels in the atmosphere. And you can say, well, that would be great for smoke plumes. I should look at that. And you can. But if you're also looking at smoke to plume dispersion models, winds are incorporated into every single weather model because they're like a basic important piece of data. And if it's going into a weather model, for plume, it's going to end up in a plume dispersion model. So you can sort of look at that and know that these winds are in there anyway. And there I am. I'm amazed that I have never actually timed this presentation and I'm 4 minutes to the good. So I'm amazed at myself, but there you go. So places that you can look at imagery. Sierra and SSEC are two government-funded institutions in the state, so they put on everything. This is College of Dupre. They're just a university, but they actually have a really good satellite site. So you can look at them. And if you want more training, I mentioned a lot of the slides came from Visit. So you can see they have all sorts of things for our height spot. And then MedEd is meteorological education. You can look at that. Also put in COMET, C-O-M-E-T, Comet, or UCAR. And it's a place you can sign up for free. And they have oodles and oodles of education on fire forecasting and satellite imagery applicable to fire forecasting and all that sort of good stuff. And with that, I am done. Thank you very much for your attention.
Thank you so much, Ron. You did a very good job getting through that, even with questions in the time allotment. So to respect everyone else's time in our 11 o'clock end, I will try to get a couple questions in. Any ones that we don't get to, we will address at our live Q&A on March 4th. So the first question is from Matt McDonald. It takes us back to slide 47. And he would like to know if the WV satellite is good for smoke, more so for high elevation smoke than low elevation smoke.
High. It'd have to be pretty high in the air. Because like say if it was low in the air, then the water vapor in the atmosphere above it would prevent the sun's rays from getting to the smoke to reflect off of it. So it'd have to be pretty high.
Thank you. Next we have from Piyush on slide 48. He'd like to know if this means MODIS AOD at 550 won't work well over snow cover.
550 microns or angstroms? Or which? What are we referring to?
Microns.
Okay, which wavelength? So you said MODIS over, you gave me a number.
550, oh geez, it's testing my whether or not I can read these right. NM, microns, nanometers.
Okay, nanometers, so angstrom. Okay, if you're looking at MODIS at 0.5 microns, 5,000 angstroms, 550 nanometers, that is correct. It will just be white. It's pretty much where snow is highly reflective. So you should just expect to see a normal visible image at that wavelength on a MODIS image. Shouldn't look any different than any other visible image. I hope I'm answering the question as asked.
Yeah, nothing else is popping up in chat yet. I'm sure if Piyush has any further questions, he'll type it in there. I have another question, which I'm assuming is from slide 69. And the question just says, is this deck available?
Brian has it, so yes. And it's all recorded. Well, yes, Brian has it. And I think I've managed to properly put a assertion against wherever I stole something from. So hopefully it's all legal. But I'll leave that to you and Brian.
Okay, I was interpreting that to mean the imagery you were showing if it's available. I might have been misinterpreting that question.
Oh.
We have one more question here. What benefits?
If you meant things like this kind of imagery, I mean, this is just like a screen grab off the workstation at Environment Canada. So not that, but it's almost all this type of imagery is available on the web somewhere in real time.
Thanks, Ron. I'm just going to answer Matt's question before I go on to the last one here. Yes, this presentation will be available to share. We will upload it to the Canada Wildfire YouTube channel early next week. I have a question here from Alex for you, Ron. What benefit would there be for using VIIR's natural fire color versus the normalized burn ratio for seeing and analyzing?
Well, you see, this is where you're talking to a meteorologist who doesn't know the natural burn ratio, so I can't tell you the answer. So I'm going to have to dump to somebody else. I say VIIR's imagery here, it's a quick glance, high impact, you can actually see, and so I say that's why I can't compare to your other products. I don't know your other product. So I don't have a good answer for you because I don't know one half of the equation well enough to answer.
Alex, I think this is a great question for March 4th when we'll have a few other experts on board for the live Q&A, so I'll save that one.
See, I don't mind appearing ignorant, so go for it. You can ask me anything.
With that, we hit 11 o'clock. So I'm going to hand the reins back to Brian here to wrap everything up. Thanks, everyone.
Okay, thanks.
Stop sharing.
I'll turn my video on. Thank you, everybody, for your interest and attendance and the questions. And I'll just reiterate that if questions come to you at 3 o'clock tomorrow morning, don't phone me, but you can send me an email and we'll collect them, or send it to Karen, and we will have those collected for week 4, which basically is the 4th of March. And we'll try and have answers somewhat prepared, or examples if there's something there. The other thing that's worth noting is I think some of the questions that showed up, for example, the normalized burn ratio, we will probably get a little bit more insight on that next week when we actually do some of the post-fire analysis work, where we're going to be looking at how, for example, the National Burned Areas Composite is generated, as well as some of the tools that can be used to evaluate the data using the Google Earth Engine for example, fire severity. So thank you again. Look forward to seeing many and perhaps all of you in a week. And special thanks to Ron. Just reiterate that Ron was one of my early teachers in satellite, and we have had long discussions about satellites over the years, as well as various other things. And so we really have appreciated you putting the time into this. So thank you kindly, Ron. And
okay, I'm going to throw out a little tidbit just to confuse you before we go. It's not satellite related. On the forecast desk, somebody once asked me, does smoke change the temperatures at night? There, you can ponder it for 5 seconds if you think what the answer is. And it turned out the answer was, according to theory, no, that smoke is fairly transparent to outgoing long-wave radiation. It suppresses daytime temperatures because it reflects and scatters solar radiation, but apparently nighttime outgoing long-wave radiation just passes through it. I would have never have guessed. There you go, my parting shot. A superb tidbit to end the day on. Thank you kindly. Take care, everyone. Stay well.